Hello everybody. Today we're going to start to talk about model building. So to do model building, you're going to need yourself a nice little data set. In this case, I have a few data sets preloaded. I have the moving data set that I've been utilizing in my other previous multiple regression videos. If you're just curious what the moving data set looks like, here you go. If you want to load this into a CSV file, you can pause the video, type it in, and play along with me if you like. At any moment, you could always pause the video and try to catch up with me. So I've loaded it as move one and I've attached it. So what I'm trying to do here in this data set is I'm trying to predict hours moved. How long it's going to take me as a moving company to move all these packages. I have a certain number of cubic feet to move. I have a certain number of large boxes to move, and I have a yes or no to whether there's an elevator available to me or not. So I see three independent variables, one dependent variable. How could I go and move on in model fitting? What can I do? The way I like to do model fitting is the all-in approach. There are three approaches, right? You could do one by one and then two by two and three by three, build it up. Or you could do all in and pull out variables as they're not important. Or you could do best subsets when you have a very large group size. When you have a very large number of independent variables, best subsets might work, but you need to really understand the algorithms of that. What I'm going to do here, this is movement, so I'm just going to call it M1. So the moving file, my first linear model, I'm just going to include everything but in the kitchen sink. We're going to include all the variables. That's the way I like to approach it, an all in at first approach. All right, and then I do a summary on my values. Everything, and as you noticed from a previous video, S statistic looks good. The T statistics look great for each individual slope. So overall, I'm very happy with this model. I can check the residuals out as I've done in previous multiple regression videos. What I'm trying to do is understand an algorithm for doing the best model. And what you need to do before you can pick the best model is you need to look at one important thing when you have so many variables. And that important thing is called collinearity and the variation inflation factor, or the variance inflationary factor. So how do you do that? Well, again, I would pause and read the little word file I brought up here. And what is collinearity? Well, when you develop these multiple regression models, we might have collinearity of the independent variables. What does this mean? Well, this refers to the situations in which two or more of the independent variables are highly correlated with each other. This becomes difficult to separate the effects of each variable on the dependent variables. And then when collinearity exists, the values of the regression coefficients for the correlated variables may fluctuate drastically depending on which independent variables are included and not included. So how do we measure collinearity? The answer is the vith, the variance inflation factor. And if we're completely an independent set, uncorrelated, each individual vith would be 1. And the set, if it's highly correlated, the vith might exceed 10. Now, of course, this doesn't tell you what the variation inflation factor is. Well, what it is a number. It's a number 1 over 1 minus r sub j squared. What is r sub j? It's the correlation coefficient when you pick one of your independent variables as the dependent variable and run it against all other options of the independent variables. So in this case, if I wanted to know the vith of feet, and of course I can run it simply by making sure I have the library car up and running the vith on car, not vith on car, the variation of inflation factor for your model, and your model is M1, you get these following vith numbers. Now notice they're all under 5, which tells me there is almost no autocorrelation, zero autocorrelation, not really much of an interaction between feet, large, and elevator as variables. Now, what I wanted to mention was, how do you get these numbers? How do we get a 4? Well, the answer is the following. What you do is you treat this as your y, and these are your x's. So what you're doing is looking at the correlation of this x as compared to these other x's, and that's a correlation of 4. That's actually not the correlation, but it's 1 over 1 minus the r squared of that. I got to be very clear in my language what I'm saying for it. And it might actually be easier right now to actually just look at the definition straight up. So again, the variance inflationary factor is a way to measure collinearity. I brought up a PowerPoint quickly. In the vith of j, the actual vith of a specific j element is 1 over 1 minus r squared j. This is that coefficient of determination that we've played around with in basic stats, using variable xj as the dependent, the y in some respects now, and all the other x's as the independent variable. That's very important. So if we're wondering if there's a relationship between the xj's, you would run this vith factor as I did in our RStudio. So again, this 4.7 is when you run that formula 1 over 1 minus rj squared. So what happens was you're looking to see if feet is related to large and elevator, all right? And the way we do that is we look at the rj squared, we run a linear model of this. Of just that. You do a linear model, so we'll call it Bob, just so we don't have to look at it. Bob, which is the linear model of feet projected by large plus elevator. Elevator. And so the summary of Bob, not boo-boo, summary of Bob gives you an r squared of 0.768. So if we do 1 divided by parentheses 1 minus that number, 0.7608, lo and behold, you get 4.18, which is that number right there. And again, that's how you get the vith, the variance inflationary factor. These numbers are important to me. They will tell me if I have picked variables that are highly correlated, which means they can affect each other's slopes, which means my projection equation would be off. So the first thing I do is I make sure none of the viths are over 5. If they are, that's the first one I get rid of. I just automatically cut it out. That's my rule of thumb. So can we make one where the vith is high? Sure. All you got to do is, let's go back to our model M. There it is. And add the interaction variable. Because when you have an interaction variable, you're automatically going to have a relationship between the interaction variable and the individual variables. So let's say that's our model M1. And so what we do now is we run the vith on M1 right away, just to see what happens. And you notice we have some very, very big numbers over 5. We have 3 numbers over 5. They're just kind of pinpointing to each other that, large seems to be highly correlated to feet, elevator, and the interaction variable. Elevator seems to be highly correlated between these. So how do we eliminate this? Because again, we don't want any of these viths over 5. So again, part of model building is step 1, throw everything in plus the kitchen sink. If you think you need an interaction variable, throw it in. If you don't know what an interaction variable is, please see my previous video. So this interaction variable seems to be causing an issue, but it doesn't have the highest vith. So the next thing I would do is knock out the one with the highest vith. And then I would rerun to see what happens. And when I rerun it, now I notice it went to a more fancier version, the generalized variation inflation, same idea. Notice it got even worse. This is well over 10, and that's really, really bad. So what are we going to do here? Well, once again, I mean, it should be obvious. When you have an interaction variable, and so I need to slow down here and pause for a second. When you have an interaction variable, obviously you're going to have correlation because they're interacting with each other. A large and elevator is related to elevator, obviously, that variable. So if you don't want any true interaction, you've got to either get rid of the interaction variable or the individual variable. So I get rid of the individual variable, and I do it, and notice my viths are fine now. My feet and large elevator, both variables are fine. They're both under 5, and so we're good now. And so this is my model I would use. I could run a summary on it and check it out. Did I need an interaction variable? Maybe, maybe not. I'm just utilizing some of the information I gave you in previous videos. If you want the interaction variable and all the rest of the variables like this, model back before, previous model before. You just have to deal with the fact that you're going to have correlation. Some people use projections even with a high correlation. They just know there is a interaction effect and they're going to deal with that effect in the prediction. Okay, so that's how we do model fitting. Notice I didn't take out any variables in that first one. I don't think I would have had an interaction term. I don't think I really would have used it. I would have done large elevator in feet and predicted hours. I think I would have been happy with that, just like my previous video. All right, so let's look at another data set, like the Cove1 data set. So the Cove data set is a data set of these, looks like 30 houses in a neighborhood. I think it's a neighborhood in Upper New York. And what you have is the fair market value of the house, and you have all these potential input variables. The property size in acres, the age of the house, the square footage of the house, rooms, number of baths, and garage. So again, my model fitting technique is pretty simple. So this would be Cove, so I'm going to call it C1 for Model 1. C1. I'm going to throw everything in there. First, you want to know what you're trying to predict. I'm trying to predict fair market value. Boom. Tilde. I'm going to utilize property size. I'm going to utilize age. I'm going to utilize house. Not that. House. The right variable. I'm going to utilize rooms. Oops, got to type it again correct. Yeah, that was correct. Rooms. And then baths plus garage. All right, so there's my linear model. And now what I like to do is I run the vith. I like to see if there's anything I can get rid of. First of all, is there any correlation? Because if there's any correlation, any relationship between rooms and foot or baths and rooms that I wasn't sure about, that can be influencing the variance and how good my model is, I want to get rid of it. So let's run the vith here. A quick scan shows that none of these are over 5, and that's awesome. So I don't have to worry about removing any of them from there. Cool. So that means I can go then to the summary. That's usually my tactic, okay? Throw everything in, run the vith to see if there's any collinearity, and then run the summary and see if all variables are important. All right, so my F statistic, p-value is awesome, which means some of these variables, at least one of these variables, is an important predictor when it comes to market value. So now I look at each and individual t value and its p-value. And so what I see is I see these 3 variables here that are not as important. You could take all of them out at once. I'm going to start with the least important variable. It looks to be the 0.75 right here, the number of rooms. Kind of interesting to me that the number of rooms. I'm just looking at the p-value, pretty darn large. I'm going to stepwise go back one at a time. That's the way I approach things. Please read up on subsets if you want to try a faster technique, especially if you have 50 variables. Taking one at a time could take a while. So doing the best subsets approach may work for that. So let's see what happens now. Boom. I took out one, and if you notice, really not much has changed. Property size is still important, house size is important, and age is 1 star important. The other 2 variables left, bath and garage, are still not important. I'm going to keep moving into my direction, which I'm doing, and that is one by one, eliminating things. Because maybe, just maybe, getting rid of one variable will influence the results of the next variable. Let's see what happens. So I get rid of garage. Seems like garage was not important when it comes to predicting fair market value. So I get rid of garage. Again, I have still triple star on acreage, triple star on house footage, and 1 star on the age of the house. Baths, once again, is not important. So let's get rid of baths now. This is, again, stepwise backwards. So we're just taking out variables one by one, coming down to a nice streamlined set of variables like I have here. So here, I'm happy with my analysis. P-value small means at least one of the combinations, one of the variables in the combination is important. I look at the t statistic for all 3 of these. They're all under 1%, which means each one of these slopes are important to me. That means they're significant variables to the prediction equation. Excellent. I'm not done here, though, but I'm done for this question. Residual analysis. Because now comes the important stuff. Do you have an outlier? You better check that. Do you need a transform? Because what if when you look at the residuals, there's clearly a cubic pattern or a quartic pattern or a quadratic pattern or a log pattern? You need to know how to transform data in case there's a pattern in your data. Please see my videos on transformations for you to learn about that or other videos. So just because I found a model I'm happy with does not mean it's a good model. I have to do the residual analysis to make sure that I check the linear, independence, normality, and equivariance. Then I also check the outliers in case there's any influential points or outliers. And then when I check in the residuals, I'm making sure there's no transformation needed. So there are still 3 more added steps in my investigation to make sure I have a properly fitted model. Excellent. But today I'm just trying to get you through the first part of it. If you look at my previous videos, I did do the residual analysis and outliers of your multiple regression equation. Once you have your multiple regression equation pared down to where you like it, that's when you go into the residuals, the outliers, and the transforms as needed. I want to make that very clear. Do not end where I ended. You must complete the previous videos, multiple regression analysis videos. Excellent. All right, what else do we have here? I also have a housing data set. So if I look at house 1, this data set I really love. There are so many data points in here. All right, you have so many interesting pieces of information. And there's some dummy variables in here. Yay! So obviously it would take me a long time to type in all these variables. So why am I bringing this up? I'm bringing this up because I want to see what happens. For example, let's look at fuel type. And does fuel type, the type of car you drive, does that tell you a lot about your total annual income? So if I want to have a model for, this was house, so this is just data from your house polled, your housing demographics, total annual income, can that be predicted by fuel type? Now I'm doing this for a reason. Fuel type is a qualitative variable, and it's not a 0-1 variable. It's a more complicated variable. It's actually got 4 different options. And so if you have 4 different options and you have qualitative variables, you really should introduce 3 dummy variables. Let's see what RStudio is going to do in this case. Let's run a summary. H1. And what we have here is RStudio says, whoa, you just gave me 3 categories. I'm going to introduce 3 dummy variables for you. Thank you, RStudio. You've made my life easier. Notice it included fuel type gas, fuel type oil, fuel type other. So I see the predicting equation, right? -3 times this variable, -3.8 times this variable, -4.5 times this variable. These are the slopes. This is the y-intercept. And so if you're saying, well, if there's 4 variables, what's the other variable, Dr. McCullum? That would be the fuel type electric, if you had an electric car. So, so the question is, actually, this is not car, this is house, isn't it? I apologize. This is the type of fuel you have in your house, gas, oil, or electric, or other. There are other types of things you can have, pellet stove, right? So we got gas, oil, and electric heat. So for fuel. So the question remains, how does one get to project what happens when you're looking at electric? The answer is when all these variables are 0. So if you go 0, 0, 0, you end up with the y-intercept. I don't know if you noticed that. When you plug in 0 for gas, 0 for oil, 0 for other, you end up at 52.5. Well, that is the pricing. That would be your estimate for your salary based on this one variable, which is your fuel type electric. If you have electric heat, we're estimating your salary is about $52,500. Notice the slopes in all these other variables are negative. The negative represents the loss in salary based on the other fuel types. If you have gas fuel, your salary will go down by $4,000, $4,500. That's what these represent, decreases. I do want you to understand these are not significant variables, if you notice in this model. So I'm guessing fuel type, bottom line, and I should have seen that from the p-value, All right, from the p-value, the field type is really not a significant variable when it comes to projecting the type of total income you have in your household. And as one would think, that makes sense. So if I wanted to do this full thing out, you would have to write in each and every one of these in there, all right, before you can do a complete analysis on this. The reason I'm bringing this example up is I wanted to further investigate what happens when you use dummy variables inside of RStudio and inside of your predicting equation. Well, RStudio makes these dummies variables for you. Make sure you understand not all variables are significant. This right here, no significant combination, and individually, none of them are good. The only thing that's good is the intercept, really, when it comes to predicting total income. All right, guys, I thank you for watching this video, and I look forward to you guys watching more of mine.